Could you describe the basic mechanisms that are at play there when it comes to, insulin sensitivity and regulating blood sugar, and then also how that can be optimized for more stable energy and better cognitive performance?
When we ingest carbohydrate, we break them down to simple sugars like glucose, and that enters our bloodstream. And we basically have our pancreas that sits close to our liver, and that produces a hormone known as insulin. Insulin is known as a transport hormone. So basically what it does is it transports glucose inside our cells from our blood. We have a very tight regulatory homeostatic set point for our blood glucose, which means basically that throughout the day our pancreas is continuously sensing where our blood sugar level is and tries to maintain that in an optimal level. For most individuals, anything less than 5 nanomole, or for US listeners, it's about 90 nanograms per deciliter. We secrete insulin in response to our meal intakes when blood glucose spikes in response to the digestion of that meal. So while we're sleeping, we're not ingesting any food. Our pancreas is still producing insulin in the background to control how sugar is being released into the system whilst we're sleeping, either from the meal we ate before we went to bed or as a consequence of fasting and our body releasing sugar from the liver, glycogen, in order to sustain our sleep process undisturbed. What exactly do we mean by insulin sensitivity? So insulin is a hormone, and our cells basically have to have a receptor that hormone latches onto. Very similar to, if anyone understands about testosterone, you have an androgen receptor where testosterone binds to. Now, when insulin binds to our cells, it causes changes to the membrane of our cells. So it's not that insulin grabs a glucose molecule and brings it inside our cell. It effectively binds to the receptor of our cell and tells the cell, okay, you're now cleared to bring glucose inside. The issue with insulin is that it's a finite hormone, in that we have a finite concentration of insulin that we make in our lifetime. So insulin actually is made as a peptide that's cleaved in a sort of pro-hormone fashion, and pro-insulin gets broken down into insulin. If it loses that capability, you then start to see issues with type 2 diabetes where you don't make enough insulin. Or if you're lucky and you catch it sort of early, you can start to see this loss of insulin sensitivity, whereby we can, I guess, implement strategies through dietary measures in order to help preserve that function of the pancreas. So in other words, we give that pancreas a break. If I was to pick one level of medicines or classification of medicines that has really improved humanity, aside from certain cardiac medicines, it would be how we've understood how the body's response to glucose is and how to intervene and improve lifestyles, like, for example, type 1 diabetes, where we can use human form injectable insulin in order to manage that person's lifetime, or with type 2 diabetes, where we can either target what we spoke about a moment ago, that's your insulin sensitivity, or target the beta cell in order to help support it make more insulin. What causes fat gain in terms of the insulin theory, and how that arose is basically when you have elevated levels of insulin, and because insulin is a storage hormone, it can also tell cells to store fatty acids. So you have a level of what we'd call lipase activity, where your body's storing fatty acids alongside glucose. And to further, I guess, make it more impressive, insulin can help transport amino acids inside our cells. And we can track this glycation process by tracking what's called our hemoglobin A1C marker in blood work. The incidence of developing type 2 diabetes today should be very low if someone is getting regular blood work and seeing how HbA1c is trending, and then responding appropriately to that trend, either through, like I said, dietary intervention or through a level of pharmaceutical intervention if it's really needed.